Okay, so welcome to Movie Statistics course. So welcome to everyone. So today we are going to discuss about descriptive statistics part 2. In our last video we discussed descriptive statistics part 1. So we discussed some basic descriptive statistics calculation methods of central tendencies, and also I think last time we started that mod value calculation. So today video also just we are going to continue that smart calculation. So I'll provide some simple examples. That is descriptive statistics part 2. Alright, so this just more examples. So we have 3 examples in this slide. So first example, we have that observation uh, 5.40, 1.10, 0.42, 0.70, 0.48, 1.10. So already you know that mod mean maximum frequency. So in this case 5.40 one time, 1.10 two times, 0.42 one time, 0.73 one time, 0.48 one time. So that means here repeated 2 times 1.10 occurred. So that means our mod value is equal 1.10. And second example, so in this case 27 3 times, 55 3 times, 88 2 times, 99 one time. So in this case that maximum frequency 27 and 55 3 times. So that means these are the maximum frequencies. So that means here we have two models, two mod values. So by model case, so 27 and 55 are our mod values. So this example, so each observation just only one time. So that means in this case we don't have any mod value. So no mod. So first one mod 1.10 and second one by model we have two models, two mod values 27 and 55, and last one no mod. So usually data set maybe contains some one mod values or some more than two mod values or two mod values, or sometimes no mod also possible. Okay, so next one, mid-range. Mid-range is rough estimate for the center of the data. It is computed by adding the lowest and the highest value and divided by 2. So maximum value plus minimum value divided by 2. That's equal mid-range. So actually this is just rough estimate. So that's why in this case just this calculation, mid-range calculations only depend to particular observation in your data. So lowest value and highest value. So and that means this is not good calculation for methods of center tendency, but maybe earlier I think for 40 years back or 50 years back people used this way, mid-range. This is a simple example. So according to the consumer report, the price per ounce in cents the barbecue flavored potato chips in sample of 6 brands 19, 27, 28, 18, 35. So in this case this 18 as minimum value and 35 as maximum value. So mid-range is equal 18 minimum value plus maximum value divided by 2, so that should be equal 26.5. So in this case that is 26.5 as mid-range. So for example, suppose if you calculate that median value, so first you have to rearrange this data in increasing order. This first observation 18, second 19, 19, 27, 28, 35. So that means in this case this we have total 6 observation. So 6 plus 1, 7 divided 3.5 observation. So that means 19 plus 27 divided by 2. So maybe there should be equal 27, 46, 23. So actually the median is the midpoint of the data. so that is 23, but in this case mid-range 26.5. That's why in this case mid-range just only we consider maximum value and minimum value. All right. So next, relation between mean, median, mode. So now already we discussed that mean calculation, median calculation, and mode calculation. So this just the snapshot. So already we introduced that skewed distribution. So this is negative skewed. So negative skewed case, this is the negative direction. So here this caveat child. So that mod value is maximum frequency. So this is that mod value, and this is the median second and mean. So mean less than median less than mod. So this case is negative skewed. And suppose this all Messa's values or Messa's tendency values are equal, mean is equal, median is equal, mod. So that's the division that is normal or symmetric distribution. So usually this is maybe some of the textbook use that word, bell-shaped curve. And third one, positive skewed. So positive skewed mean this is maximum mod, always maximum mod. And mod value greater than median value, greater than mean value. So there's a division called that is positive skewed. So they're in this positive direction. Okay. And so I have given that here when the distribution is negative skewed, so mean less than median less than mod, or positive skewed, mod less than median less than mean. And the distribution symmetric or bell-shaped curve, this all values are equal. And actually in this case this median is the midpoint. Okay, and mod is the maximum frequency. Okay, but in this case actually this x-axis as random variable values. So you know this mod values random variable values. Okay, so actually in this case this mean is lower and median second one, and mod is higher value. In this case mod is higher, low value, median is second one, mean is higher. Okay, so actually this is based on this information, this every time median is lies between mean and mod. Okay, all right, the mean and median are not always used to identify the shape of the distribution, and that's why already you know that extreme point also affected for mean calculation but not affected for median calculation. So that distribution is not good method. All right, so next, methods of variation. So methods of variation case, we are going to discuss about several methods of variation. So first important methods of variation, range calculation and standard deviation calculation and variance calculation. All right, first we'll roughly discuss why we used it to methods of variation. So methods of central tendency gives us methods of where the center of the data is, but this is not sufficient to characteristics of the data. For example, so this data set A contains 50, 60, 70, 80, 90. B contains 69, 69, 70, 71, 71. So suppose if we calculate that mean value, both situations will get 70. And the first set of data is more widely dispersed than second data. So that means in this case, suppose if we calculate mean value 70 and also median value also 70, and that's why this is already ordered data. So we have 5 observations, so third observation as median, so this is the third observation as 70, so that is median. So mean value also 70, median value also 70. But in this case, suppose if we calculate the range value, so that means that range of the data, so here 90, this is 50, so 40, in this case 40, in this case just range 2. So that methods of variation is need to characterize the data set. So select measures of variation such as range, mean absolute deviation, usually we denote as MAD, and variance and standard deviation are discussed following slides. Alright, so first range. So range is simplest measures of variation. The range is difference between the maximum value and minimum value of the measurement. So this is already everybody know that range is equal maximum minus minimum, high value minus low value. So based on this earlier data, this range of data set A 40, data set B true. So this is 40 mean 90 minus 50 and 22 mean 71 minus 69. So data set A has more variability. Range is simple measures of variability, but it is used only two values from the data set and ignores all other values. So maybe the situation where the range is important. So that situation maybe we can use that methods of variations. Alright, second mean absolute deviation. So usually we denote as MAD. So in this case mean absolute deviation from mean, that means just calculate the average of absolute deviation from mean. So that means population mean absolute deviation. So population case we consider capital N number of observation or capital N number of individual in population. So summation of absolute value x minus mu. So summation of absolute value x minus mu divided by n. Here important, this is absolute value. So absolute value means this is always positive. So for example, suppose absolute value -2. So this is equal +2. So suppose if you calculate the summation of x minus mu, that should be equal to 0. So here don't forget that absolute value. But in real life, this is not uh, this is not useful because there's populations parameters are unknown. So in sample case we consider simple n number of observation in your sample. So that mean absolute sample mean absolute deviation is computed as summation of x minus x bar absolute value divided by n. Okay. So next slides, I'm going to discuss some simple example. Alright, so this example, random sample is 7 and we have players height. So they're given here 7 observations. So first we have to calculate that sample average. That's why you know that mean absolute deviation calculation, summation of x minus x bar. So first you have to calculate that x bar and then you can divide it by n. So and also don't forget that absolute value. So in this case, this average means sum of all observation divided by n. So that should be equal 6.67. So next, if we calculate the mean absolute deviation, so this is that formula summation of x minus x bar. So first observation x minus corresponding average x bar absolute value, and second observation minus x bar, third observation minus x bar, the fourth observation minus x bar, up to last one minus x bar. So here don't forget that absolute value, and then divided by total number of observation, here n number of observation. So that should be equal 0.2443. Okay. All right. So next, variance calculation. So variance also very important methods of variation in methods of dispersion calculation. So the variance is the measures of spread of the data around the mean. So formulas for variance differ slightly depending on whether we are using sample or entire population. So usually we have some standard notation. So the population variance is denoted as sigma lowercase sigma square, that is variance, and sample variance is denoted as s square. So and also population variance, we calculate the sigma squared, x1 minus mu, so that means population average or population mean square plus x2 minus mu square plus x3 minus mu square up to last one. So and divided by total number of observation. So this is that formula, summation of x minus mu all this square divided by n. And as sample variance, so sample variance formula is slightly different. So this numerator term just look like in a population case, this is observation minus sample average square plus second observation minus sample average square plus up to last one. Here in this case we consider sample n number of observation, so and divided by here n minus 1. Earlier in this case population case we divided as big N, total number of individual in population, but in this case symbol n minus 1, that is important. And so this is formula we can try it. S squared is equal sample variance is equal summation of x minus x bar square divided by n minus 1. So this is our formula, so we can use that formula in our calculation. And also we can simplify that formula in another version. So usually our initial formula summation of x minus x bar all the square divided by n minus 1. So suppose if we use that expansion a minus b all the square, a minus b all the square is equal a square plus b square plus 2 times ab. So suppose if we use this expansion, we will get that x square is equal 8 into summation of x square minus summation of x all the square and divided by n into n minus 1. So suppose if you need this proof, just comment in this video. I will explain that proof in maybe next video. So in this case, maybe in variance calculation case, directly we can use this formula or otherwise our initial formula. So usually we call there is initial formula is a direct formula. So and also this is we call shortcut formula. Okay, next standard deviation. So you know that the relationship between standard deviation population variance. So actually the standard deviation should be equal to square root of the variance. So suppose if we consider population standard deviation, you know that population variance we denote as symbol sigma square. So population standard deviation should be equal to sigma. So that means square root of sigma square. So that should be equal to sigma. And similarly, sample standard deviation we denote as s. So it's square root of s squared. So already we know that formula, s squared formula. So just square root of the summation of x minus x bar squared divided by n minus 1. Or otherwise, we can use that another formula, summation of square root of n into summation of x squared minus summation of x all to the square divided by n into n minus 1. So there is a sample standard deviation, but in this case maybe later we will introduce that calculation. So you can calculate by using GI83 or 84 calculators. You can find that sample standard deviation values, or otherwise maybe we can use that formula too. So the variance is easier to comprehend, but the standard deviation is more direct used through Zscore calculation, empirical rule, and Chebyshev inequality, and so on, to name few. And also maybe later we will discuss that distribution section. We will discuss normal distribution. So normal distribution case, two parameters. So first parameter average or mean, and second parameter standard deviation. So maybe most of the time we use the standard deviation, not variance. Some situation we will use the variance. So this is very important. Alright, so there's simple example. So amount of total snowfall in Minnesota in 2011 is is estimated from sample of 10 different locations. So in this case we consider 10 different locations, and also they're given total snowfall So this that actually these are just discrete observation district values. So suppose in this case we are going to discuss we have two different equations. So I'm going to discuss each situation. First we will apply that first formula, and then later we will apply that second formula, and definitely we will get the same answers in each situation. So in this case, the question find the sample variance and sample standard deviation using both main and shortcut formula. Main formula mean our initial formula, and shortcut formula is second formula. So first we are going to use that main formula. So main formula, first we have to calculate that sample mean. So you know that our main formula, summation of x minus x bar all this squared divided by n minus 1. So first we have to estimate that x bar. So x bar is equal to summation of x divided by n. So sum of all observation divided by total number of observations. So in this case we have 10 observation. So this should be equal to 16.0. So x bar is equal to 16.0. So then we will apply that main formula. So main formula f squared is equal to summation of x minus x bar all this get divided by n minus 1. So maybe in this case maybe we can just create the table form. That's the easy way, or otherwise maybe you can calculate one by one. This doesn't matter. So this is that observation. So this just calculated x minus x bar. So in this case already calculated x bar is equal to 16. So 19 minus 16, so that should be equal to 3, and 18 minus 16, that should be equal to up to last one 13.5 minus 16 negative 2.5. So then calculate these square values. So 3 square 9, 2 square 4, 1.5 square 2.25 up to negative 2.5 square 6.25. So in this case that is important, this is that square value, so this is always positive, not negative. Okay, so sum of, and also suppose if you calculate sum of this column should be equal to 0. So that is theoretically we prove that summation of x minus x bar is equal to 0. So suppose if you get any answers is not equal to 0, so that means you did some mistake here. So you have to make sure your all calculation. So in this case this column should be equal to summation of x minus x bar all this square. So that should be equal to 33. So we can write that variance is equal, s squared is equal, these values, this summation of x minus x bar squared divided by n minus 1. So in this case n is equal to 10, so n minus 1 is equal to 9. So s squared is equal to 33 divided by 9, so that should be equal to 3.667. So this is that variance. So suppose if you want to calculate that standard deviation, you have to take square root value. So that should be equal to 1.915. Note that the sum of the deviation from mean is always 0. So that is summation of x minus x bar is equal to 0. So okay, so next we are going to discuss that, so apply that shortcut formula. So you know that shortcut formula s squared is equal n summation of x squared minus summation of x all this squared divided by n into n minus 1. So summation of x all this squared mean summation of x all this squared mean, in this case just calculate this summation of this column, sum of all these observations, that should be equal to 106, so 60. So summation of x all this squared means 160 square, and x square, so each observation square value, so 19 square 361 up to 13.5 square 182.25. So sum of this column should be equal summation of x square. So next apply that formula and plugging that numbers. So here, so we'll get that answer 3.667. So this is exactly the same for our previous calculation. So then maybe you can take square root value here. So that should be equal to sample standard deviation. So the sample variance or sample standard deviation was the same calculated by original formula, but the shortcut formula used less computational steps. So in this case, suppose if you use this formula, so maybe your computational way is easy. Okay, So, but maybe you can use that anyway, this formula or direct formula, whatever. So it doesn't matter. You will get exactly the same answer. All right. Next, coefficient of variation. So in order to compare the variation in two or more different distribution when the unit of measurement is not the same, we can use that coefficient of variation. So actually this coefficient of variation will use that comparison purpose. So suppose if you need to compare any two set of different sample variation, so that situation maybe you can calculate the coefficient of variation and compare the coefficient of variation, then we can make the conclusion. So coefficient of variation expressed as a standard deviation as percentage of the sample mean. So that means this is a formula: coefficient of variation is equal standard deviation divided by mean into 100. So usually we do this as in percentage sign. So first calculate the standard deviation ratio between standard deviation and mean, then multiply by 100. So your answer in percentage sign. Okay. And also maybe in population case, population standard deviation divided by population mean. In sample case, sample standard deviation divided by sample mean. That's not just only different, but already you know population case, most of the distribution, population variance or population standard deviation and population mean are unknown, but we can estimate that parameters from sample. All right, so this is the simple example. The raiding post in Grand Mesa is the small family-run store in Colorado. Grand Mesa region contained many good fishing lakes. So the raiding post sells spinners, a type of fishing lure. The store has 8 different types of spinners. The price in dollars, so there is that price. So in this case, suppose if you want to calculate the coefficient of variation, first we have to estimate that x bar and standard deviation. So sample mean and sample standard deviation. So maybe sample mean, just you can apply that formula. So we'll get that answer 2.14 and sample standard deviation 0.22. So then next apply that coefficient of variation formula. So 0.22 divided by 2.14 into 100, so that should be equal 10.28 percentage. So we can interpret this value 10.28 percentage. So this means the standard deviation of spinner's price is only 10.28 percentage of the mean. So this is that interpretation. And also similarly, already you know that population case, we can use that formula. Alright, and also in this case, in this section, we'll introduce that Chebyshev inequality. So the Chebyshev inequality also very important for maybe later we will discuss some empirical rule and normal distribution case. So maybe we will use that Chebyshev inequality is the basic foundation of the developing empirical rule. So this is the inequality of theorem. So this is introduced by Chebyshev. So case one of the statistician. For the population, Chebyshev inequality applied to any distribution. So any distribution maybe symmetric distribution or negative skewed distribution or positive skewed distribution, whatever. So which state for k should be greater than 1, at least 1 minus 1 over k squared into 100% of the measurement will fall between mu minus k sigma and mu plus k sigma. Or otherwise, we can say at least 1 minus 1 over k squared, 100% of the measurement will fall within a k standard deviation of the mean. Okay, so there is population case. Similarly, sample case, Chebyshev inequality applies to any number of data. It states k should be greater than 1, at least 1 minus 1 over k squared into 100% measurement will fall between x bar minus k times s and x bar plus k times s. So here important k should be strictly greater than 1, not equal to 1. That's why maybe not equal case, this that meaningless. 1 minus this goes to 0, so that is meaningless. Or other hand, we can say at least 1 minus 1 over k squared, 100% of the measurement will fall within k standard deviation of the mean. So this is the sample case, hence this is that population case. So suppose if we put k is equal to 1, or k is equal to 2, that's why here k is strictly greater than 1. So k is equal to 2. So suppose if we calculate this one, 1 minus 1 over 2 square, so that should be equal 1 minus 1 over 4. So that means 3 by 4. So 3 by 4 into 100, that should be equal 75. So we can say at least 3/4 or 75% of the data values will fall within 2 standard deviation limit. So that means x bar minus 2 times s and x bar plus 2 times s. So here not the case, not necessarily integer, maybe k is some possible, maybe some decimal point too. Okay, but k is strictly greater than 1. That is the important condition. Alright, so this is the Chebyshev inequality. So this is the simple example, so just application of Chebyshev inequality. So let the mean price of houses in certain neighborhood with 50,000 and standard deviation 10,000. Find the price range for which at least 75 of the houses will sell. So in this case, maybe we can apply the Chebyshev inequality. So we know that Chebyshev inequality case 75% of the data values will fall to standard deviation limit. So 2 standard deviation limit mean x bar minus 2 times s, x bar plus 2 times s. So suppose if you calculate that x bar minus 2 times s, 50,000 minus 2 times standard deviation 10,000, so that should be equal 30,000. Okay, and x bar plus 2 times s, 50,000 plus 2 times 10,000, so that should be equal 70,000. So actually this is that 70,000, that's just mistake. Okay, so 70,000. So can say at least we can say at least 75% of houses will be sold in the area will get price range from $30,000 to $70,000. So this is that simple application for Chebyshev inequality. So next slides we are going to discuss that just extended that empirical rule definition from that Chebyshev inequality. Alright, so Chebyshev inequality, we can apply any distribution, symmetric or non-symmetric distribution. So this empirical rule, just only we can apply the symmetric or bell-shaped curve. So when a distribution is symmetric or bell-shaped, approximately 68% of the data fall one standard deviation limit, and 95% of the data fall two standard deviation limit, and 99.7% of the data fall three standard deviation limit. So one standard deviation mean x bar plus or minus s, and two standard deviation mean x bar plus or minus 2 times s. This is x bar plus or minus 3 times s. So actually in this case first also given this is that based on sample, and also maybe we can consider population case. There's that one standard deviation limit mu plus sigma or mu minus sigma, and mu plus or minus 2 times sigma, mu plus or minus 3 times sigma respectively. So, and this is also very popular, but in this case that's an important condition. Your distribution must be symmetric or bell-shaped curve, or otherwise we cannot use that empirical rule. That is important. So this that picture diagram. So this that first 68% of the data fall one standard deviation limit, and two standard deviation limit 95% of the data, and three standard deviation limit 99.7% of the data. So here important, your data or your distribution must be bell-shaped curve or symmetric. Alright, this is a simple example. So a random sample is 7 NBA players height, so we have 7 observations here. So we can calculate the x bar values and variance and standard deviation. This is already we discussed in previous slides. So in this case, the x bar value is equal 6.67, And suppose if you calculate standard deviation 0.3114. So in this case, first we have to estimate that variance, then you have to take Zscore value. So 0.3114 as standard deviation and 6.67 as mean value. So in the application of empirical rule, assuming that the distribution is bell-shaped, so that is very important condition. So we can say in this case 68% of the data falls one standard deviation limit. So one standard deviation mean value minus one time standard deviation value, and mean value plus one time standard deviation value. So that means these intervals 6.3586 and 6.9814. So we can say 68% of the measurement for this interval, that interval between 6.3586 and 6.9814. And approximately 95% of the measurement are between 6.67 and 2 times 6.67 minus 2 times 0.3114. So that means two standard deviation limit. So that should be 0.6.0472 and 7.2928. So we can say 95% of the data lies between 6.0472 and 7.2928. And similarly, we can say 99.7% of the data for three standard deviation limit. So that should be equal, that interval 5.73 and 7.6042. Alright, so this is the simple application for empirical rule. So in this case, that empirical rule application case, first you have to make sure your data is symmetric or not. So suppose symmetric, you can apply that empirical rule any situation. But not symmetric case, we cannot use that empirical rule. Then suppose if you apply that empirical rule, you'll get wrong conclusion. Alright, so this is another example. So IQ scores have bell-shaped distribution with mean 100 and standard deviation 15. So first question, what percentage of the scores are between 70 and 130? So in this case, that mean value 100 and standard deviation value 15. So in this case, our question, what percentage between 70 and 130? So based on this information, this is 100, so 100 plus 2 times 15 should be equal 130, and 100 minus 2 times 50 is equal 70. So in this case, maybe we can use that empirical rule. So two standard deviation limit. So you know that 95% of the data for two standard deviation limit. So and also in this case, they given this general mean, so that means this is a population mean, so that interval 70 and 130. So by empirical rule, we can say 95% of the scores falls between this interval. Okay, and second, greater than 115. So 115 mean mu plus sigma, so there is one standard deviation limit, but empirical rule, 68% of the data falls one standard deviation limit. So that means this is 115. This is 115. So actually this is equal 85. Okay. So by empirical rule, there's that 68%. But in this case, our question, what percentage of the scores are greater than 115? So that means this area. So this is 68. So this is 68%, but this is symmetric. So remaining 32 scores are outside. Outside means less than 85, greater than. And also this is symmetric. So they should be equals 32 divided by 2. So that means 16%. So you have an answer, 16% of the scores are greater than 115. Okay. All right. Okay, so next is circle calculation. So this is one of the important measurement. So in this case also we'll use that average and standard deviation. So standardized scores is also called Zscore, for an observation is obtained by subtracting the mean from the observation and then dividing the result by the standard deviation. So usually we denote as Z score value. So in population case, this individual observation minus mu minus divided by sigma, population standard deviation. And sample case, x minus x bar divided by s. So that means individual observation minus average sample mean divided by sample standard deviation. So in this case, the Zscore measurement of the number of standard deviation that the data values for the below mean or above mean. So that means maybe some situation this x bar greater than individual observation, some situation x bar less than individual observation, some situation x bar is equal like individual observation. So we have three different categories. So first category Zscore is positive, so that means actual value is greater than mean, or actual value is lower than mean, that's the deviation of Zscore value negative, or both are equal, the actual value is same as the mean, so that's the deviation we'll get that Zscore is 0. So we have three different categories. Okay, all right, so this is a simple example. The human body temperature has mean of 98.2 Fahrenheit and standard deviation 0.67 Fahrenheit. So suppose if you need to convert the 97.5 Fahrenheit to a Zscore, so there is observation 97.5 and average 98.2. So 97.5 divided by 9.98.2 divided by standard deviation. So the standard deviation should be equal 0.62. Actually, this maybe this typo, this 0.62. All right, so that is equal to negative 1.129. So that means Zscore value is equal to negative 1.129. So that means Zscore is possible, maybe 0 or negative or positive. And also maybe conversely, you can apply this equation. Suppose if you know the Zscore value, you can identify other terms. So a student scores 85 on the test, where standard deviation 3. So Zscore 85. And students, score 85, Zscore was 2.33. So find the test average. So in this case, we have to calculate the x bar value. So and already they given here standard deviation is equal to 3 and Zscore is equal to 2.33 and individual observation value is equal to 85. So suppose just substitute here, you'll get that and the x bar is equal x minus Zscore value multiplied by standard deviation. So that should be equal to 78.01. So that is that x bar. So in this case, maybe we can apply that formula for any direction. Okay. And also this is important, that's interpreting Zscore values. So the Zscore value interpretation case, you know that Zscore value may be possible 0 or negative or positive. So in this case, yes, we consider this cutoff point negative 2 and positive 2. So suppose our Zscore value greater than negative 2 or greater than negative 2 or less than greater than positive 2 less than negative 2. So that's the division we call that value or that observation unuseful. So suppose this values lies between negative 2 and positive 2 or equal negative 2 or equal positive 2. So that's the division equal, that is not an unuseful value. So that means ordinary values. So this interpretation is maybe useful. So first we have to suppose if you want to identify your observation unusual observation or not. So first you have to calculate that Zscore. So then maybe you have to make sure your Zscore values lies between negative 2 and positive 2 or equal negative 2 or equal positive 2. So that situation we can say that is not unuseful or ordinary value or otherwise unuseful observation. All right, so this is that interpretation. So okay, so next section, measures of position. So this is very important measures in summary statistics. So in this case, we are going to discuss these three important measures of position: quartile, percentile, and finally we'll discuss that deciles too. Alright, so misses are due to position of the measurement relative to overall distribution. So that first, in this case, that measures of position, sometimes some of the text will use called quantiles. Okay, so in general, the measures of position known as quantile. Here we will discuss several quantiles such as quartiles, deciles, percentile. So quartiles are the three partitioning measurement when the overall distribution divided into four equal proportion. So just we divided, for example, this is the data, this is that minimum value, this is that maximum value. So just we divided four equal proportion. So this is that quartile, first quartile, this is first quartile, second quartile, third quartile. Okay, so and also usually we denote the S notation. Q, big Q1, Q2, Q3, first quartile, second quartile, third quartile. So Q1, first quartile, is the value of which 25% of the measurement are false, lower or equal. So that means this is that first quartile cutoff point. So in this case, this is that 25% of the measurement falls this interval. And second quartile, 50% of the measurement. That means Q2, the second quartile, is the value of which 50% of the measurement lower or equal. But in this case, you know that median is the midpoint of the distribution. So special case, this is Q2 is a special case. So Q2 is actually median. Okay, and third quartile, 75% of the measurement are lower or equal. Okay. So in order to calculate quartile, we can first compute the median of the whole data, which is second quartile. Okay, so the median. Already you know that median calculation. Then Q1 is the median of the data below Q2. And actually this is very popular method for Q1 calculation. So median of the lower half of data. So that means, for example, this is the data. So just be divided for partition. So this is the minimum value here, maximum value here. So first calculate that midpoint, median of the whole data. So that means this one. So that is Q2. Okay. So then you have to calculate, suppose if you want to calculate Q1, so this is that Q1. So in this case, that Q1 is equal median of the lower half of data. So that means median of this data. Okay, and similarly upper half of data, so median of the upper half of data should be equal Q3. Okay, so this is Q1 calculation. Okay, so and also most of the statistical packages or statistical softwares, or even though your calculator also use this approach, this calculation approach, but maybe later we will discuss another way. So maybe suppose our data more than 30 observation or 40 observation, so that situation maybe manually, if you want to calculate that Q1 Q3 values case, we have some standard method or standard formula, then maybe you can use that formula. So suppose if you use formula, maybe sometimes you will get that answer maybe it's just different, but it is not affected for your final conclusion. All right, so there's the simple example. So find Q1, Q2, Q3 for this data. So in this case, we have 8 observation, 2, 3, 4, 6, yeah, 8 observation. So first, or you have to rearrange this in data in increasing order. So that is the first step. So and calculate that Q2, that is step 2. Q2 calculation. So in this case, n is equal to 8. So 8 plus 1 divided by 2 should be equal 4.5. So 4.5, the fifth value or fifth observation should be equal median. So this is the first observation, second observation, third observation, fourth observation, this fifth observation. So 4.5 mean lies between fourth observation and fifth observation. So here, so that means we have to calculate this average of these two numbers. So 13 plus 15 divided by 2, that should be equal 14. So next, this that median So lower half of data mean this is the lower half of data, this is the upper half of data. So Q1 is the median of the lower half of data. So median of the lower half of data mean in this case just we have 4 observation. So 4 plus 1 divided by 2, 5 divided by 2, 2.5. So that portion here. So that means 6 plus 12 divided by 2, that should be equal 9. And similarly here 18 plus 22 divided by 2, 20. Okay. So this is a simple example. And next, decile. Decile, this earlier we discussed the quartile. So quartile we divided 4 equal proportion. Similarly, deciles are the 9 partition measurement when the overall distribution divided into 10 equal proportion. The deciles are usually we denote as D1, D2 up to D9. For example, D2, the second decile, is the value for which 20% of measurement are lower or equal. Okay, and similarly D5 means 50% of measurement are lower or equal. So actually that is equal Q2. That's median. And similarly percentile calculation. So percentile calculation, this decile just we divided 10 equal proportion. This percentile just we divided corner equal proportion. So for example is 17. The 17th percentile is the value for which 17% measurement are lower or equal. Alright, so this is the standard way for calculate that quantile values. So first step, you have to arrange this data in increasing order. So that means you have to rewrite the data in smallest to largest. So suppose already rearrange the data in increasing order, so you can ignore that step 1. Next, compute the locator. So usually this locator we denote as L. So n plus 1 is number of observation n plus 1 times p. So p means this proportion is the corresponding the percentage of interest. For example, suppose if you want to calculate Q1, p should be equal 25, 0.25, 0.25. And suppose decile 7, your proportion is equal to 0.70. Okay. And step 3, locate Lth measurement is order of data. Interpolate whenever L is not integer. Maybe some situation L is not integer, some decimal point, we can use that interpolate method. So maybe later we will introduce that interpolate method. So note that slight variation is method use different orders but use different introduced. Here will produce more suitable methods of portion. So actually maybe your sample size is less than 30 situation, we can use a basic definition. Q1 is equal midpoint or median of the lower half of data, and Q3 is equal median of the upper half of data. Or otherwise maybe more than 30 observation or 40 observation, you can use this way in Q2 and Q1, Q3 calculation too. Okay. Alright, so this is the simple example. A random sample of 7 NFL NBA players height. So they're given here and 7 number of players height. So find the 25th percentile. So this order data, so just rearrange this data in increasing order. So next calculate that location. So 7 plus 1 is 0.25 second value. So that means Q1 is this 0.6.39. Okay. And also another example, find the second decile. So second decile mean locator case this p is equal to 0.20. So this is the order data. So this is the locator 1.6. So 1.6 mean first observation, this is the first observation, second observation. So 1.6 lies between first observation and second observation. So that means you have to write on here 1.6.23, that is first observation, and calculate this difference between first and second. 6.39 minus 6.23 into multiply by this is 1.6. So just ignore that first leading point, just consider the decimal point 0.6. Okay, so actually this is we call interpolate method. Okay, so actually in this case first you have to calculate that 1.6th position. So first observation, second observation minus first observation into this remaining decimal point. Okay, 0.6. That's it. All right, so last section, this box plot. So box plot is the one of the graphical display for the data, but in this case the box plots depend on some measures of position calculation. So first you have to calculate the measures of position Q1, Q2, Q3, then we can draw the box plot. So actually this is very popular in just to identify that outlier points or shape of the distribution. A box plot plotted either horizontally or vertically, so we can draw that plot maybe horizontally or vertically, whatever. Okay, so first we have to estimate the 5 number of summaries. So 5 number of summaries mean minimum value and maximum value, Q1, Q2, Q3. So already you know that minimum in lowest value of the data set and maximum highest value of the data set. So if you draw the box plot, first step you have to calculate this 5 number of summary. So actually that is the first step. So this is the procedure. So find the 5 number of summaries for the data values. So there is maximum, minimum, Q1, Q2, Q3. Okay. So then draw the horizontal axis with scale such that it include maximum, minimum data values, or otherwise maybe you can draw the vertical axis too. Okay, so it just doesn't matter. So draw a box whose vertical side go through Q1 and Q3, and draw the vertical line through the median. So draw the line, the minimum data value, the left side of the box, and line from the maximum data values, right side of the box. Okay, so this is the procedure. So actually you have to follow this procedure, then you can get it that box plot. Or otherwise maybe some of the text would use box plot or Zscore plot. That's also meaning box plot. That's in the name. And also you know that this main purpose for box plot is identify outlier points. So this outlier identification, first you have to outliers should be investigated carefully. That is very important for your data analysis. Often they contain valuable information about the process and investigating the data gathering and recording process. So first we have to calculate that these intervals Q1 minus 1.5 times IQR. So that means this is IQR means interquartile range. So Q3 minus Q1. So suppose if you calculate this interval, so actually this is we call inner fence and outer fence. Any data point outside of this interval we called that is outlier. Okay, so this outlier identification case, first we have to draw the box plot and then calculate that this interval, so inner fence and outer fence value. Then you can check whether any data values or any data points falls outside of this interval. That is important. All right, so this we call inner fence, this outer fence or upper fence. Oh, okay, so lower fence or upper fence, so otherwise maybe we can say inner fence, outer fence. It is doesn't matter. That means also values less than lower fence value or greater than upper fence value are considered outliers. And also in this case, line may be extended from the box to smallest and largest value that are not suspected outliers. So maybe suppose no outlier case, you can extend the line from box smallest to largest, maximum value and minimum value. Okay. So this is one of the example. So construct the box plot for NBA players height data. So median is 6.73 and Q1 is 6.39 and Q3. So then maybe we can draw that curve. So this is the minimum value, this is the maximum value, and this is that Q1, this is Q2, this is Q3. And also if you calculate that lower fence and upper fence values, so 7.765 upper fence value and lower fence value is 5.565. So actually in this case, this whole data point lies between this interval. So that means in this case there is no outlier points. Okay, hopefully everybody understands that outlier identification Alright, so this is the end of the example. So in this case, this is our data. So first we have to rearrange this data and calculate Q1, Q2, Q3. So I think this is already done, this Q3 calculation, Q1, Q2, Q3 calculation. And also calculate IQR into quartile range and low fence and upper fence. So in this case, one of the data point, this is 50. So 50 is outside of this interval. So that means there is outlier points. Okay. All right. So and also this is maximum value, this is the minimum value, this is Q1, Q2, Q3. And also after ignore that outlier points, so this is that maximum point, is that right? Yes. All right. So also given that interpolation method, so maybe you can use that interpolation method in your calculation. So suppose if you want to find out any position in fraction decimal point, or suppose for example 1.6 position or 2.8 position or 2.1 position, so that's the division, maybe we can use that way. And I also given one simple example, so you can use that example too. And also maybe you can use your calculator, GI83 or 84 calculator. So in this case I also given that step by step. So just you have to first you have to enter the data in L1 column. So press stat menu and press move calculate and press one variance stat and press second L1. So then it displays for every items, every summer statistics calculation. Okay, so in this case important this SX means sample standard deviation. So sigma x means population standard deviation. So this is actually not useful. So maybe most of the time useful that SX values and X bar values, sample variance, same standard deviation. Suppose if you want to calculate sample standard variance, first you have to identify your calculator provided just only standard deviation, not variance. So then you have to take square value. Okay. So this is that ending position of today's presentation. So thanks for your watching. So please don't forget subscribe my channel. So see you on next video. Thank you so much.